Hi friends, so today we are dealing with the sixth module. In this, we are going through the topic concurrency. So in concurrency, we'll be dealing with the thread and synchronization. Okay, so we'll move to the topic right. First topic is concurrency. So what do we mean by concurrency? Concurrency means if two or more processes are active at a point of time, then we can say that those processes are concurrent process. Okay, so if two or more process or program, we can say, if they are active at a particular time, okay, then we can say that they are concurrent programs. Okay, and you know that what do you mean by synchronization? Synchronization means control of order of operations occurring in different threads. It's called the synchronization. All those topics you already know. Okay, and synchronization is implemented by two way. First one is spinning, the other one is locking. Okay, okay, so synchronization is implemented in two ways, spinning and locking. We'll be dealing with it in depth later. Okay, so we'll move to the next slide. So how concurrency can be included in languages? Okay, uh, languages, how you can use concurrency. Okay, for languages, some languages already uh, they will be concurrent languages. Okay, so already that languages will be supporting concurrency. Okay, there are some languages which support concurrency. You can see that Algol 68, ADA, etc. are the examples for language that support concurrency. So that is the first type. The second type, you can say that during the compilation time, some extensions can be added so that they can be uh, you can impart concurrency to that language. Okay, so actually that is not an feature of the program, but you are adding some extension to the compiler. Okay, you are adding some extensions to the compiler so that that feature called concurrency can be imparted. Okay, so that's second point how we can implement concurrency to the language. The other way that we use, most probably we'll be using this way, that is external library. So for languages which are not concurrent, for example, if you are thinking about C program, it is not concurrent. Okay, so C program, Fortran, etc. are not concurrent, but we will be using some external library so that it can be made as if it is a concurrent language. It can work as if it is a concurrent language. So in three ways you can just implement concurrency. The first one is already the language do have the feature. The second one, the compiler will be supported with some extensions, and then the third one, the language will be having some external libraries which can be included in the program so that the feature called concurrency can be included. Okay, external libraries you will be using OpenMP. OpenMP is an example for an external library which can be used to import concurrency in both Fortran and also in C. In C also you can just implement for concurrency using OpenMP. Okay, in the best concurrent program using the concurrent language is the best one. Okay, so the best one is using an explicit concurrent language, and external libraries also is used, but the minimum uh, thing that is used is compiler supported extensions. Okay, so we move to the next slide. So all of you know about what a thread is. So I'm not dealing with what a thread is. You know what a thread is. Okay, thread is actually an alternative form of schedulable unit of computation to the traditional notion of process. Okay, also it can be called as a lightweight process. Okay, so you all know what a thread is, so I need not explain much about this thread. So this is how a thread will look like. Okay, Through the architecture of thread, you can see that there will be m processes and n threads. Okay, m processes and n threads. Okay, so the process will be having n threads maybe. Okay, there is no single count. It can be n number of threads for a process. Okay, and a lot of process will be there. So all the process will be having some threads with it. Okay, so when the scientists were dealing with the architecture of thread, the first thing that they came to the mind is one process having one thread. So if there was 5 processes, then there will be 5 threads. Each process will be having one thread. Likewise, that was the extreme condition in which the scientists were thinking about. But the problem was, this is actually the goal of thread is to use the same resources or share the resources that a process have. But when you are using this like this, it won't be sharing the resources, right? So actually the concept of thread is lost in this architecture when you are using one process for one thread. Okay, also a process will be having only one thread. So actually the goal of using thread will not be accomplished. Okay, so this architecture will not be used, and also you know that for a multiprocessor supercomputers and all, this might work, but for a uniprocessor system, this won't work because it requires a lot of resources, and the actual goal of it is not accomplished when you are using one process for one thread. Okay, the another extreme case that they were thinking about was for n number of threads, all the threads will be inside one process. Okay, so if you are dealing with a lot of threads, like n threads, all the threads will be controlled or will be residing inside one process. So that was another architecture, which is another extreme architecture that came to the mind of scientists. But the problem of this is, if a process is having a lot of threads in it, so like this, a process will be having a lot of threads. The main problem is that if one of the thread will go for a system call, one of the thread will go for a system call, then what happens? Actually, the process need to get stopped. Okay, so the process need to get stopped because one of the thread is go for system call. So when the process stops, what happens? No other threads will be able to execute because all other threads is inside this process. Okay, all other threads comes inside this process. So what happens? Actually, uh, when the process itself is getting stopped while go for in a paused, or we can say that we'll go for a wait condition while going for a system call, no other threads can work because all the threads result in this process. So that also, that extreme condition cannot be used for a thread architecture. That's why the scientists came for this architecture, that is M process on N threads. M process on N threads. That means one process will be having N threads. Likewise, a lot of process will be there, and also each process will be having N number of threads. Uh, may not be and need not be same. Okay, for one process there can be 3 threads, another process there can be 2 threads. That depends. Okay, that means actually it will be like end-to-end relation, like this. Clear. So this is the architecture. You can see that for one process, you can see one process. You can see that in the first process there are k threads. Okay, and the process M, the process M, you can see that there are A, B, C up to L threads. Okay, so that's what you mean by M process and N threads. So one process will be having n number of threads, another process will be having another set of threads. Okay, so just deal with this thread architecture. Now we'll be dealing with the thread creation. How thread creation happens, or we can say that how actually the concurrency is imparted in different languages. Okay, so there are 6 options. Okay, so when you are asked about thread creation, okay, or how, if you are, how concurrency system. or how thread are created dynamically. Which are the various ways in which the thread are created dynamically in a concurrent system. If the question is like that, we have to give this all these 6 options. Okay, so there are 6 ways to create a thread dynamically. The first one is co-begin. The second one is parallel loops. Third one is launch until operation. Uh, Fork slash join. I hope you all know about what is fork or join. The third one, the fifth one is implicit receipt, and the last one is early return. Okay, so these are the 6 options in which a thread can be created dynamically, dynamic thread creation. Okay, 6 ways. Okay, I hope you all know about fork and join, so I won't be explaining much on fork and join. Okay, so if you need to go know much about fork and join, you can just go to the uh, uh, operating system subject. Okay, so that you can understand what a fork and join is. Okay, so we'll start with the first one, that is co-begin. Okay, so co-begin is actually a keyword that is used in Algol 68. Okay, Algol 68 will be using co-begin. Co-begin is used in Algol 68, uh, and also okay, Algol 68 you will be using co-begin. And the specialty of co-begin is that whatever statements that you are writing in co-begin will be executed concurrently. What all statements will be writing in co-begin will be executed concurrently. That is, in this you can see that in this co-begin, this is a starting of co-begin and this is the end of co-begin. In this, you can see that there are end statements, 1 to n. End statements are. So all these end statements will get executed concurrently. Okay, so that's how co-begin works. Okay, so for a live example, we can go to this example. Okay, live example, we can go to this example. Okay, so in co-begin, you can see that there is one more difference in this example, that is there is another begin and end. Okay, so here there is one begin and end. Okay, and also there is co-begin and end. Okay, so here is the co-begin ends here and this begin statement ends here. Okay, so if you need to add some statements that need to be executed sequentially, if you need to add some statements which need to get executed sequentially, you will be using begin end. Okay, so whatever written in begin and end will be executed sequentially. Okay, that you understand that. I hope so. Okay, so in co-begin, the specialty is that whatever statements you write, it will get executed parallelly. So the first statement is a function call. So P is a function. Okay, so the P will get executed. Okay, then there is a begin and end. Okay, so what all inside this begin and end will be executed sequentially. So in begin and end. So whatever written inside the begin and end will get executed sequentially. Okay, and there is another function called that is S. So S will be, since it is inside co-begin, S also will be executed parallel or concurrently. Okay, so stay. So here we can see that there are 3 parts or 3 functions which will work concurrently. The first one is a function called P. It may have some definition somewhere else. So that is one thread that will be executed concurrently. And there is something called begin and end. Okay, so here you have written what all you need to execute inside this. So begin and end, all the statements inside this will be executed sequentially, but actually this total begin and end, that statements inside all the begin and end will be parallel to function P and function S. Likewise, function S will be executed parallel. Okay, so that's about co-begin. So co-begin, the specialty of co-begin is if you are using co-begin, all the statements written inside the CoBegin will be executed parallelly. Okay, and we told about using external libraries, right? So we have already told that in C we will be using OpenMP. OpenMP is an external library which is used to import concurrency in C. Okay, so here you can see that you are using OpenMP. Now instead of CoBegin, okay, it's actually a version of CoBegin. Okay, so for that you will be writing something called pragma OMP sections. Okay, this is written instead of CoBegin. Instead of CoBegin, we will be writing pragma OMP sections. Okay, OMP means OpenMP. Okay, so we will be writing pragma OMP sections. The specialty of this is each section will be executed concurrently. Okay, so OMP section, this may have n number of steps, and also this have m number of steps. Okay, so actually the first section and the second section will be executed concurrently. So which is similar to CoBegin. Okay, in CoBegin all the statements will be executed concurrently. Likewise, in pragma OMP sections, each sections will be executed parallel, or sorry, concurrently. You cannot use the word parallelly, you have to use the word concurrently. Okay, so this is another way of using CoBegin. Clear? Now we'll move to the next topic. So first one was CoBegin. The second one is the parallel loops. Okay, parallel loops. Okay, the specialty of parallel loops is each iteration will be executed concurrently. In parallel loops, the specialty is that each iteration will be executed concurrently. Okay, so for example, let there be a function called a. Okay, so I hope something is this is pragma OMP parallel. How this is how you write it. Okay, so explain this. I am writing just a function. Okay, so for that I'll be writing hash pragma OMP parallel 4. Okay, I write the first step. Then I'll be writing a for loop. Okay, so I'm writing for I equal to 0, I less than 5, I plus plus. So this is a for loop. And inside the for loop, I am calling a function a of I. Okay, so if I'm writing like this, each iteration will be executed parallelly. For parallel, each iteration will be executed parallelly. That is, a of 0 will get executed in concurrent to a of 1. Okay, and which will be concurrent to a of 2, which will be concurrent to a of 3, which will be concurrent to a of 4. Okay, so 0 to 4, all each iteration in CoBegin it was like each statement was executed parallel, but here each iteration will be executed parallel. Okay, so a of 0 will be executed parallel to concurrent to a of 1, which will be executed in concurrent to a of 2, which will be executed concurrent to a of 3 and a of 4. Each of this a of 0, a of 1, a of 2, a of 3 and a of 4 will be different threads. That's how the concurrency will be imparted. Okay, so that's about parallel loops. Okay, so we dealt with CoBegin and also we dealt with parallel loops. Okay, so you can see that statement by statement parallelism implemented in parallelism in for loop. Okay, now next one is launch elaboration. In launch elaboration, actually what you will be doing is you will be creating a function, something called a procedure. Okay, and the specialty of this procedure is that there will be no parameters. So actually what you are doing is here you will be creating a parameterless procedure. Okay, and the specialty of this one is each recursive call of this subroutine will create different thread. Each recursive call of this subroutine will create each recursive call of this subroutine will create concurrent threads. Okay, so here only the recursive calls will create what threads. Okay, so we'll be writing a function. So there will be a procedure, and the procedure, the specialty of the procedure, it is a parameterless procedure. Okay, parameterless subroutine. Okay, and inside this procedure, the procedure will be called again and again, and each time the procedure is called, or the subroutine is called, a recursive call is for a subroutine, and for each recursive call, each thread will be created. Okay, for each recursive call, thread will be created. I hope it is clear. Okay, so in languages like Ada, thread is created as a subroutine without parameters. Okay, so core begin was the in these statements were used. Parallel loops were the in which looping statement all iteration will be executed or created as a different thread, and longit elaboration in which all the recursive calls will be each recursive call will be different various thread. Okay, different thread. I hope it is clear. Now next one is fork and join. I hope you all know about fork and join. Okay, the difference of fork and join is fork is used to create a thread, while join is used to uh, wait for the completion of previously created thread. Okay, so fork and join. There are two parts, fork and join. Okay, so I'm not explaining it much. We'll just go through this figure. So this is actually the figure of all other except the fork and join. So if I'm dealing with parallel loops or co-begin, or you can say that longitudinal elaboration, what all it will be. Okay, so it will be having the same starting point, right? It will be having the same starting point and will be having the same ending point. That is, in co-begin, the starting point is where the co-begin statement starts, and the ending point is where actually that co-begin ends. Likewise, for loop, so for parallel loops, actually the starting is the first statement. Okay, starting of the loop, and all the iteration will be stopped with the ending of the loop. Okay, so all those things will be having the common starting point and common ending point. But for fork and join, there won't be a common starting point or a common ending point, because uh, all will be an individual threads, and each threads will be joined. Okay, so after completion of one thread, it will wait for the other thread to complete finish it. Okay, so there won't be any common starting point or common ending point for fork and join. Okay, so that is the main difference between fork and join and all of that. Okay, so this is how fork and join is used in Java. You will be using extends thread. Okay, extends thread will be used. I hope you know about fork and join in Java. Okay, you have already done lab in using fork and join. Okay, in Modular, to create a thread, you will be writing T equal to fork of C. You will be explicitly defining it, fork of C, and also you will be using join for the join purpose, join of T. Okay, likewise in Ada there is no explicit call for fork and join operations. Just moving through it. Okay, there will be no explicit uh, operation for fork and join, but it happens inside. Okay, that means if this is a function and you will be creating an object of that, so it will be like a you will be creating a thread. Okay, so you will be creating a thread. Okay, oh, sorry, No, you will be creating a thread by declaring it. Okay, as a declaring a class object. Okay, and in C sharp, what you'll be doing is this is a constructor, right? So this is a class image render. So this will be having the same name. That means this is a constructor image render, same of same. Okay, so inside this class, this is a constructor here, and this is a function which need to be executed as a thread. So this is a function which need to be executed as a thread, which is inside the class. So what you will be doing is you will be creating a class object. So for creating a class object, you will be using image render, the class name, object name equal to new image render, as if you will be using in Java. Okay, and instead of in Java you were using extends thread, right? Extends thread or runnable. So you will be using so. But instead of that, what you'll be using is you'll be creating an object of thread. Creating an object of thread. The specialty is that for this thread, for this object, as an argument, you will be sending new thread start and also the class object. Okay, sorry, not the class object, the function that need to be executed as thread. The function is rend object dot foo. Rend object dot foo will be passed through it. Great. So in C sharp, what you'll be using is to create a thread. What you'll be doing is you'll be creating an object of the class, and also you'll be creating a thread class, object of a thread class, and to which you will be passing that function. Okay, function that need to be executed as a thread. I hope it is clear. So this is how in C sharp we will be creating for function. Okay. Now the next topic is implicit receipt. In implicit receipt, what happens is actually uh, what happens is that uh, the thread creation happens, or it is actually like RPC, remote procedure code. Okay, it is like actually called remote procedure code, in which the client will be initializing the thread. Okay, the client will be initializing or sending the request communication, and the thread will be created inside the server. So the client will be sending the request, and the thread is actually created inside the server. Okay, so actually client is the one which starts the communication, and the thread is created inside server. Okay, to remote server. So in implicit receipt code, it will be actually like RPC, remote procedure code. Okay, so it will be actually like RPC. A request comes from the client, and the new thread is created, and the thread is created in the server system. So the server system actually binds the communication channel, okay, to the local of the thread body or the subroutine, so that it can just convey the results to the client. Okay, so it binds communication system and also local thread body or subroutine. So actually the thread is created inside the server, that is the highlight point. It works as a it is an RPC code. Okay, and uh, all both the operation like fork, join, etc. operations on the thread will be requested by the client, and actually the thread space will be in the server. That's all. Okay, so actually the binding operation allows client to perform fork operation in server address space. Okay, so actually there will be binding. So implicit receipt. That is the fifth one. Now we'll move to the sixth one, that is early reply. This is another one which is called the early reply. Okay, in early reply, actually what happens is uh, listening. Actually, if I am writing a subroutine, if I am writing a subroutine or a function A, okay, so A is a function and B is another function. Inside A, I will be calling a function B. Okay, so A is a function, B is a function, and inside the function A, I am calling a function B. So what actually happens? Actually happens is like you will start with A. Okay, so A is here, B is here. We will start with A. When A calls B, it will hand over the communication to B. Then it executes B. After executing B, it will go for A, and A will continue for the execution. This is how the execution will happen in the uh, normal subroutines. Okay, normal subroutines. This is how the execution starts. Okay, execution happens. But in early reply, what happens is when B is called first, initially the B will give a reply or will return a value. Okay, B will return a value. So what actually happens is A and B are two functions. So A is called. Okay, then A will be calling B. At the time of B, when B is called, it initially what happens? It will return a value so that A can execute, and parallelly B also will get executed. Okay, before B get executed, it will return a value to A so that A can get executed, and parallelly B will get executed. So that is the early reply. Okay, so the caller need not wait for calling. Okay, that means the calling returns a value before it finishes the execution. So that's how early reply works. I hope it is clear. Okay, so next topic is synchronization. Synchronization is actually how the process get executed. Okay, concurrently, how they are getting executed. So there are a lot of threads, and all these threads how they are getting executed. All this comes under synchronization. For synchronization, there are two types of synchronization. The first one is busy wait synchronization, and the other one is non-blocking synchronization. Okay, so in busy wait synchronization, what happens is there will be some condition so that the process can access some resources. Okay, so that there will be a variable called x. Okay, so the specialty of this is if x equal to 0, the resource can be accessed by a process, and if x equal to 1, the resource cannot be accessed by a process. You all know about this semaphore, mutex server, and all, right? Likewise. Okay, so what happens is if x equal to 0, the resource can be accessed. If x equal to 1, resource cannot be accessed. Okay, so what actually does is if a process P1, P2, P3, etc. comes, need to get executed. So what happens to get executed? It will check whether x equal to 0. To acquire the resource, it will check whether x equal to 0. So P1 will check whether x equal to 0. P2 will check whether x equal to 0. P3 will check whether x equal to 0. Okay, when x equal to 0, the process can access the resource, and it will set x equal to 1. Okay, so here there is a problem actually. Okay, so what happens is initially let's so be x equal to 0. Initially let x equal to 0. Okay, so initially x equal to 0 and P1 comes. So here the P1 comes. P1 check whether x equal to 0. Yeah, x equal to 0. So actually what can P1 can access the resource. Okay, so P1 can access the resource. So when it accesses the resource, it have to set x equal to 1. But before that, before setting x equal to 1, what happens? P2 comes. So before setting x equal to 0, P2 comes. So P1 has already left. After checking with the x equal to 0, so reading. Okay, so P1 reads x. P1 reads x. Before setting x equal to 1, P2 reads x. So what happens? P2 also feels that x is equal to 0, so it also can access the resource. Okay, by the time P1 sets the value of x equal to 1, so what happens? P1 will set the value x value as 1. So P1 get the resource. And also what happens? Since P2, when P2 read the value of x, it is equal to 0. So again P2 will set the value of x as 1. Will set the value of x as 1. So what happens? Both the process will come to take the same resource at the same time. Okay, so this shouldn't happen. So instead of this, to make another, so to avoid this contingency, what happens is it will use BCV synchronization. We'll use something called test and set. It's the name is test and set, but actually what happens is set and test. What happens is actually set and test. Okay, so the name is test and set, but actually what happens is set and test. So set and test. What happens is, okay, so in this process, so it is called the spin lock. So this is called the spin lock. It will be using test and set. Okay, so here what happens is initially the value of x equal to 0. Okay, initially what P1 does is, instead of checking whether x equal to 0, okay, instead of checking whether x equal to 0, okay, it will first set x. That means instead of checking whether x equal to 0, it will set x. So first of all, what happens when P1 comes, P1 converts x as 1. First of all, P1 is converting x as 1. Before checking x, it will be storing x as 1. It will be setting x as 1. First it will set. Okay, now it need to test. How it will test? Actually, P1 test the value of x with the previous value of x. So if there is a change, then it means that P1 can use the resource. Clear? Again I will say, initially the value of x will be equal to 0. So when P1 need to use this resource, first it will come and it will set the value of x. Set the value of x is, it will change the value of x from 0 to 1. First it will set that. Only after that it will test. Okay, only after that it will test. So first it will set, then it will test. What it will test? It will test whether the current value, whether the current value is same as the previous value. It will check whether the current value is same as the previous value. If it is same, then it means that it cannot access the resource. If it is same, it cannot access the resource. If the current value and the previous value is different, then it can access the resource. Okay, so what happens? In the same scenario, if I say first the initial value of x equal to 0, then P1 comes. Okay, the scenario that made the problem was first the P1 reads, then P2 reads, then P1 set, then P2 set. So when we executed this scenario, there was a problem. Okay, so instead of this, what happens is when P1 comes, it will set x. So the value of x is 1. It will compare to the previous value 0, and previous value was 0. So it can access the resource. So when P2 comes, when it checks, when it sets x, the value of x will be 1. And it will compare with the previous value. Since already P1 has set the x as 1, for P2 the previous value of x is also 1. So there is no change in x. So P2 can't access the resource. Okay, so that is called test and set. So that is called test and set. Okay, hope it is clear. And it returns a value true. Okay, so that's how it works. Now, the main problem of this is test and set. The main problem of test and set is when all the process need to give two comments. Okay, whether the process get the resource or not, all the process need to get two resource, to give one write operation and also one read operation. Okay, so each process needs any resource. Okay, for each process, what happens? There will be one write operation, one read operation for each resources. For each resources, it will be passing one write operation and one read operation. So two operations need to be passed for each request of the resource. So that means there will be a large amount of communication on the processor. So the processor need to spend more time for setting and testing. Okay, so whatever works it need to execute, there won't be any time. It need to give more time to for this setting and testing. Okay, test and set. Clear. So that is a one problem. So for that, to overcome that, what we will be doing is initially when it comes. Okay, initially when it comes, it will go for. Okay, initially when it comes, it will go for one test condition, test and set condition. Okay, after that there will be only test condition. There won't be any set condition. Okay, so first it will check for test and set condition. If it is not, it cannot acquire a lock or it cannot access the resource, then it will go for only checking. No testing, no setting will be there. Okay, so initially there will be test and set condition, test and set. After first test and set, for all process only one test and set will be there. Okay, after that test and set, what happens? It will be only checking. It will check. It will check. It won't set the value. It will just check whether it is available or whether the value of x equal to 0. So it is actually the mixture of first and second options. Okay. So this type is called test and set. So this is called test and set. And this one time for the when the process comes first, it will test and set. After that, it will only set or it will only test. Okay, so first it will check for test and set. Only after that there will be only test, no more set. So it is called test and set. I hope it is clear. So that's another thing. Okay, and also there is to reduce this contingency, there is something called backoff. In backoff, what happens is if a process didn't get a resource, it will be asked to wait for a particular amount of time, so that it won't be polling it again and again from the next second on this. Okay, so it will be asked to go for sleep for a particular amount of time. Only after that it can just check whether it can access the resource. I hope it is clear. So that is called backing up. So there is another thing called back. Okay, so in spin lock we thought about three things. The first one, it was set and test. So okay, set and test. So actually the name is test and set, but actually what happens is set and test. Okay, so test and set, first one. Then to for test and set, the problem is all the process need to have two operations. It need to pass two operations, so the communication will be a lot of communication will be there. So we will be introducing another one, test and set, in which the first option for when a process comes for the first time, it will test and set. When it comes again, if it doesn't get the resource, it will come again. At that time, it won't test and set. It will only go for testing. There will be no setting operations. That is called test and set. The last one is backing off, in which when a process doesn't get a resource, it will go wait for some amount of time. Okay, so that is back off. I hope it is clear. Now we'll be moving to another one. So the first one was spin lock. So we were uh, dealing with synchronization. Okay, so now mm, synchronization using polling. Okay, so the first one was spin lock. Now we'll be moving with barriers. Okay, so the next one is barriers. What happens in barriers is that it makes sure that all the threads are executed. Okay, in barriers, what happens is it make sure that all the threads are getting executed. Barriers. So actually, what happens is there will be you'll be giving some points. Okay, okay, some points. So if thread 1 reaches that point and thread 2 hasn't reached that point, thread 1 will have to wait until all other thread reach that point. Okay, so it will be some point will be set. Okay, some checkpoint will be set. We can call it as something called, you know what a checkpoint is. Likewise, a point will be set in the process. There will be a point. Okay, so if a thread execute until that point, it will just wait so that all other threads will get executed in that point. Okay, so that is called barriers. That is called barriers. Okay, so actually what happens is there will be a counter. There will be counter, and the initially the value of the counter will be n. Actually, if there are n threads, there will be counter, and the initial value of counter will be n, where n is the number of threads. Okay, when first thread reaches the point or reaches the barrier, what happens? Counter will get decremented to n minus 1. When the second thread comes and reaches the barrier, it will be moved to n minus 2. Likewise, all the threads, that is the first and second thread, will be waiting till all the other threads, all the other n minus 2 threads get to that point. So until the counter is becoming 0, until the counter reaches the value 0, the threads which have reached that point will be waiting. Only when the counter gets 0, again the counter will be initialized with n and all the threads will get executed again. Again there will be another point, so the n will be reduced. Okay, I hope it is clear. So, till that barrier, it will make sure that all the threads are getting executed to that point. Okay, so when the first thread gets executed to that point, it will have to wait until all the threads get executed up to that point. Okay, so that is called barriers. Now we'll move to the next topic, that is non-blocking algorithms. Okay, actually this is a non-blocking algorithm. Okay, in non-blocking algorithm, what happens is you will be using something called CAS. Okay, CAS means, actually it means that it means compare and swap. It means compare and swap. It means compare and swap. Okay, so here what happens is, so this is the automatic how a locking system actually works. How a locking system actually works. Actually, if I need to acquire a lock, what happens? It will read one value. Okay, read the value of h2r1. Okay, and if need to, here the value of x need to be changed. Okay, so x is the resource. So if it is acquired a lock, then r1 will be copied to x. The value of x, previous value of x, is copied to r1, and a function will be executed. The resultant value will be copied to r2, and the value of r2 is copied to x. Okay, so the x will be having the new value. Here x is the resource. In the last condition, x was a condition variable, but here the x is a resource. Okay, x is the place where the changes occurs. X is a resource. Okay, that's the difference. In the last condition, it was just a variable for checking the checking condition to access the resource, but here x is a resource. Okay, so in CAS compare and swap, what happens is r1 equal to x. Okay, so there will be no lock. Here we can see that instead of this, actually we are replacing this locking statement with this CAS statement. So there is no lock here. Okay, so to make sure that no other process has accessed that resource, if another process has written something, the value of x will be changed, right? If P1 is a process which is using x, P2 is another process which is using x. If P1 has used the value, and if it has returned the value to x, the value of x will be changed. Okay, so P2 can access the value of x. Okay, and after execution, if P2 compare the value of its previous value and the value of x now, if it compares the value of x, it can understand whether another process has accessed that resource or not, right? Okay, so if P1 hasn't changed the value of x, initially the value of x will be same, and now the value, initial value and the value of x at this time will be same if P1 hasn't written anything. But if P1 has written something, initial value of x will be different, with the value of x, which is the value of x now. Okay, at this point. Okay, so actually that comparing is happening here. Okay, so what happens, instead of log, what you will be doing is, initially, listen here, initially the value of x will be stored in R1. So R1 is a register, the initial value of x will be stored in R1. Then the process executes with R1. Okay, so the P2 will be executing with the value R1. After R1, okay, after R1 get executed, after R1 get executed, after the function get executed with the value R1, okay, what happens? You know that R1 was the previous value of x, right? It will compare R1 and x. It will compare the value of x and R1. It will compare the value x and R1. That is the value of x. Now, what is the value of x? That is x. Previous value of x before execution of P2 starts, that is R1. So it will compare x with the previous value, the current value of x with the previous value of x. If the value of x hasn't changed, that means no process has accessed x, right? If the value of x hasn't changed, that means no process has accessed the x. So what happens? If it no value changes, no change in value of x is there, then what happens? It will copy the value R2 to x. Okay, so actually the return value is R2. So P2 has to write or replace the value of x with R2. Okay, only if the value of x hasn't changed, that is the current value of x and the previous value of x is same, only then it will copy the new value to the x. I hope it is clear. So instead of creating a log, it will just check the value of x, whether it has changed or not. If the value of x is changed, then that means that some other process has used the value of x. Okay, if the value of x is not changed, that means no process has used it, or no process has written anything. So it can change. So what happens? If the value of x hasn't changed, it will replace it with the new value. I hope it is clear. Okay, so in non-blocking algorithms, we will be not blocking any of the process. There won't be any locks. In this system, there won't be any locks. In the other system, there were locks, spin locks were there. Okay, barrier also there were locks, so that all other process thread gets executed and this thread will be blocked. But here there is no blocking. Okay, so it just compare and swap. If the value of previous value and the current value are same, it will swap. That means no process has changed. I hope it is clear. Okay, so this is a generalization of this. So it will just repeat until success. So if a process need to access a resource, it will repeat this loop until CAS will be success. If CAS is success, that means the resultant value has returned into the resource. That means the process has executed or the thread has executed. So until CAS, this will get repeated. So that is generalized series. Okay, this is how it will be implemented. Okay, so this is all about synchronization. So I hope you understood the lecture. If you have any doubt, you can just ask. Okay, thank you.